Two quick things. First thing, we've already written, actually, the formula for the electric potential due to a point charge. We had it before when we were talking about potential energy per unit charge. We said that electric potential was defined to be potential energy per unit charge. And we wrote the potential energy using the Coulomb force. K, Q, Q2 over R divided by Q2. Division by R, remember, because we're talking about potential energy. The Q2's cancel, and we have K, Q over R. The electric potential due to a point charge. Electric potential is like gravitational potential, and electric potential energy is like gravitational potential energy. We keep track of all the points that have the same gravitational potential energy with a contour map, with a topographical map. This curve is the collection of all the points that are all 1,440 meters above sea level, which means they're all at the same H for MGH. They all have the same GH, same gravity environment, it's the same planet, same height above the surface of the planet, same GH. And GH, that's like gravitational potential, not energy, gravitational potential. How much energy? How much gravitational potential energy? How much mass do you have this high above sea level? MGH. Here's another example of a topographic map. We have these points of higher elevation, higher gravitational potential. Think greater electric potential too. Here's a different picture. Let me zoom in a little here. We're plotting elevation. And then here's a topographic view where we're keeping track of all the points that have the same elevation. All the points that have the same GH, all the points that have the same gravitational potential. These are curves, contours of equal potential. We could call them equipotential lines. Here's a different picture. You look at this one quick. Is it a topographic map? Sort of looks like one, but then we notice a couple things. It's got the letter Q on it, and it says something about volts. It is very much a topographic map, but it's a topographic map for electricity. What is the electrostatic terrain? How much electric potential do all these points have What is the strength of the electric environment, E? And what is the elevation, D, delta X, away from sea level? Q1, Q2, Q3. Here's a contour labeled -5. Here's a contour labeled 0. Here's a contour labeled +5. It looks to me like Q3 is positive. That's an uphill. It looks to me like Qs 1 and 2 are negative. Those are downhills. They're like sinkholes. Kind of like drains in the bathtub. And Q3 is like the spot where the faucet is dripping in. You can imagine being the rubber duck in this electric environment. And if somebody dropped you here, let's say here at point I, you would roll downhill, down the electric contours this way. Oh, shit. This way towards the spot between G and K. This way, because that's the direction of steepest change in electric elevation. Then you would start to head this way, and then maybe this way, and then might fall towards one of the drains. Like if this were a topographic map of, physical terrain, you could imagine taking a ball and setting it somewhere here and watching it roll downhill. Same story. The path that ball takes downhill, the path that the rubber duck makes through the water, that's the trajectory line. How does it travel? What is its path? We can track the trajectory lines, the field lines, electric field lines, and we can track the contours of equal potential. Pictures like this are what we're going to try to develop in Wednesday's lab. That's all I've got for now.